Welcome to learning logistic regression in R and Excel. Now, if you take this course, here's what you can expect to learn. The characteristics of binomial outcome variables, such as buys versus doesn't buy and recovers or get worse. Any kind of situation in which you might have to make a decision between two or more alternatives is an appropriate kind of context for this course. You'll also learn about the reasons that binomial outcome variables create problems for standard analysis procedures such as simple and multiple regression. You'll see how simple transformations that involve odds ratios and logarithms can solve the problems that binomial outcomes bring to regression analysis. Now, I use Excel in this course mainly to show you what goes on inside logistic regression's black box. You'll be able to see the intermediate calculations involving those odds and those logarithms. And I use R to show you how to reach the end point of the analysis quickly so that you can skip over those intermediate kinds of calculations. There are a couple of preliminaries that you probably ought to see to before you take this course on logistic regression. There are a couple of basics. One of them is you should know how to install and use R and its packages. And you should also have some background, at least, in least squares regression analysis. Now, if you don't have those clubs in your bag, there are a couple of courses that you might want to take a look at to get up to speed. One of them is Up and Running with R, which does a good job of telling you how to install R and how to install and use its various packages. The other one is R for Excel users, which has a fair amount of content involving the analysis of least squares. Now, this course includes a variety of exercise files, and you can use them in different kinds of ways. One is to just follow along with the steps that I show you in the video so that you can actually create R analyses and Excel workbooks that conform to what you see on the screen. You can also use them to find out more about functions. Excel has an awful lot of worksheet functions, over 300. For example, the log natural function. And R has quite a few functions as well, such as mlogit and glm. You'll be able to find out more about functions that I use in the course, as well as related functions if you do follow along using the exercise files. And you can also use the exercise files as a platform or a jumping-off place to explore more involved ways, more sophisticated methods to apply using logistic regression analysis. Suppose that you're confronted with this sort of situation. We have in column A variable labeled buys product, and that simply means, does a person buy this product or does a person not buy the product? And we're in a situation here where we would like to predict that sort of behavior on the basis of two other variables, the price of the product and the buyer's age. And most people, when they're faced with this sort of question, think of multiple regression. And in multiple regression, as you probably are aware, you use more than one predictor variable, here price and buyer's age, to predict or forecast another variable. Normally, that other variable is a continuous variable. For example, you might want to predict a person's weight from a person's height. And we'll take a closer look at that in just a minute. In this situation, we don't have a continuous variable. We have a variable with only two values, 100% and 0%. It's binary. It's called binomial. And that can cause some problems for standard linear regression, whether multiple regression or not. And it has less to do with the mathematics that underlie regression analysis than it has to do with the nature of the scale on which the outcome variable, this buying behavior, is measured. Here it's just two values, and therefore you can get problems with using the standard regression approach on this sort of outcome variable. It has to do with whether or not some of the assumptions that underlie regression analysis, whether or not they are conformed to or violated. And let's take a closer look now at the normality assumption. Now, here I've got approximately 1,000 observations consisting of the height of people and their weight residuals. I'll explain what the residuals are in a moment. But what we're doing is predicting weight on the basis of a person's height. The weight is, of course, a continuous variable, as is height. And what we do when we predict weight from height using regression analysis is we take the x values, the predictor values, and we run them through a regression equation, and the result of the regression equation, the person's predicted weight. So we've got two measures of weight. One is an actual observation, and the other is the predicted weight on the basis of the regression equation. If we subtract the predicted weight from the observed weight, we have what's called a residual. And there will be a residual for each person who's gone through this analysis. And the normality assumption asks the question, do we have a normal distribution of residuals at each point along the x value axis? Now, this chart that I've created over here contains all the residuals, all 1,000 residuals, and it approximates a normal curve pretty closely. But that's really not what the normality assumption in regression analysis is looking for. It's looking for the distribution of the residuals at each point along the x-axis. So if we took a look at, for example, 62, those people whose height is 62 inches, and we redraw the chart, and we've got something that doesn't look as close to a normal curve as we were just looking at, but it's not too far off. And I would think that if I were to double the size of the sample, maybe even triple the size of the sample, that the residuals just for the x value of 62 inches would look even more close to a normal curve than these do. We can take a look at another one. Let's have a look at 063. And the chart looks even more close to a normal curve than it did at 62. So at this point, I would want to take a look normally at more of the x values to see how the residuals are falling out. But at this point in this case, I'm pretty well satisfied that we've met the normality assumption for the weight residuals. Now, the reason that this is important is that we base other statistics, such as the standard error of estimate and confidence intervals around predicted values. We base those on these residuals, and we ring in frequency distributions, reference distributions such as the normal curve and the t distribution. And if we are presenting values of residuals that are not normally distributed to a reference distribution that is normally distributed, then we've got problems. And we wind up with misleading errors of estimate and misleading confidence intervals. But in this case, we're probably okay, in part because the outcome variable is a continuous variable. And in the next lesson, we'll take a look at what happens when that. In the previous lesson, we took a look at a linear regression analysis that predicted weight from height. And we saw that the continuous outcome variable, that being weight, conformed to the normality assumption such that the residuals for weight were normally distributed at each different level of the predictor variable, height. Now, here we're predicting the probability of buying a house in columns A and B, given different amounts of annual income. So in column A, I've just indicated whether the person winds up buying a house or not buying a house. And of course, that translates to a probability of purchase of 100% or 0%, depending on the person's actual behavior. We want to forecast that probability of purchase on the basis of the person's household income. So the person in row 2 is showing $97,000 worth of income, and the person in row 3 is showing $68,000 in annual income, and so forth. Now, given those two pieces of information, we can derive a regression equation that predicts a probability of purchase on the basis of income. In Excel, you would use trend to do that, the trend function. And the trend function takes as its arguments the predicted variable here in B2 to B31 and the predictor variable here in C2 to C31. So predicting the probability of purchase on the basis of income. And the trend function begins by calculating exactly what the regression equation looks like, the intercept and the coefficient. And it returns for each record involved in rows 2 through 31 the result of the regression equation, a predicted probability of purchase, and we can subtract that from the actual value of purchase, and we can get then the residual. So 100% is the actual probability of purchase. 100% in this case is also the predicted probability of purchase for a residual of 0. In other words, we predicted this person's behavior perfectly. On the other hand, for the person in row 3 who does not buy the house, the regression equation tells us that he is 39% to purchase the house with an income of $68,000. And so if we subtract the predicted probability from the actual probability, we wind up with a residual of minus 39%. Now, given those residuals, I've charted them here on a graph that has income as its horizontal axis and is the predictor variable, and the residuals on the vertical axis, and those are residuals of the outcome. And you'll notice that it looks very different from the charts that we looked at when we were predicting weight from height and charting the residual weights against height. What we've got here is two parallel lines. In this case, they're declining diagonally. And this is exactly the kind of pattern that you will always get with a binary variable as the outcome variable. What we're doing in calculating the residual is subtracting the forecast value called y hat here, y with a caret over it, and that's the predicted value, and we're subtracting it from either 0 if the person's probability of purchase was actually 0% because he did not buy, or it's 1 minus the predicted probability, and that would be 100% minus the prediction for a residual of 62%. Given that we are subtracting from 1 and from 0, we are going to wind up with these two diagonal lines. These represent the people who actually wound up buying the house and have a 1 or 100% as their actual purchase probability. And these represent the people who wound up not buying the house. We're subtracting the predicted probability from 0. Now, we do not have a normal distribution here. For the value, let's say, of approximately $65,000 in annual income, what we've got is 2 points, this point here and this point here. And when a residual can take on only 2 values, it cannot be normally distributed. So the presence of a binomial outcome variable gets us into trouble with the normality assumption. We have 1 or 2 more assumptions to take a look at, and we will do that in the next 2 lessons. The first one is the linearity assumption, and we'll take a look at that next. Both linear regression and the topic of the series of lessons, logistic regression, allow the predictor variable to run all the way from minus infinity to plus infinity. There are no artificial or arbitrary limits that can be set for that variable. In this example, for instance, we're predicting, once again, the probability of purchasing a home at different income levels. And if we go ahead and use standard linear regression to make those predictions via, once again, Excel's trend function, we wind up with a straight line on the chart, and that's the linear aspect of linear regression. The problem is that given that we need to allow the predictor variable here, income, to get as small as it can, perhaps $0 per year, or in some cases, negative income, all the way at the other end to much larger amounts of income, $150,000 a year to millions of dollars a year. Well, the result is that our predicted probabilities of purchase get out of line. For example, if you'll note at the left end of the income scale in the chart, down around $50,000, the predicted probability is less than 0. If you take a look right here at an income of $50,000, according to these data, the probability of making a home purchase is minus 20%. Similarly, at the other end of the scale, up with an income of $150,000 or more, the predicted probability of a purchase exceeds 100%. And we can't have that. That flies in the face of what we want probabilities to tell us. Now, mathematically, it's fine. The point is, however, that logically it makes no sense. So what we'd like to find is some way of allowing the predictor variable, here income, to extend all the way across its possible range from 0 on up to plus infinity without violating our logical expectations of how probability should behave. And that means, in this case, staying between 0 and 100, staying within that range regardless of what the level of the income is. Now, we can take a look at that here. This is really how we would like to see the trend line associating income with probability of purchase behave. The blue line, as you notice, is curved. The black diagonal line is still straight, and that's what we're looking at over here in this worksheet. It's represented by a black line here. The blue line shows us how we would like our predictions to behave. Notice at the lower end of the income scale here, down around $40,000 at the left side of the horizontal x-axis, the blue line does not slope as sharply as it does in the center. It flattens out, and in fact, it approaches 0% on the vertical scale, but it does not fall below 0% the way that the straight trend line does. Similarly, at the right end of the scale, up around $160,000 in annual income, the blue line flattens out again and does not exceed 100%. This is the kind of thing that we are looking for in our projections. There are three tools that logistic regression uses to get to this outcome. One of them is the use of odds rather than probabilities. As you probably know, odds are closely connected to probabilities, but they do behave differently, and we'll be taking a look at that. The second tool is logarithms. And if it's been a while since you looked at logarithms, we'll take a brief look at how they behave and how they can help us constrain the projected probabilities to a range that goes from 0% to 100%. Logarithms and odds are important for that. And thirdly, rather than using the correlation approach that is taken by simple regression and multiple regression, we'll be using maximum likelihood techniques, which get us to the same place via a different route. This is essentially the same example as in the previous lesson. In this case, though, I've left the linear regression trend line off the chart so that we can focus on the logistic regression trend line, the S-shaped curve that you see in blue on this chart. And we're looking at, once again, the fact that we do not have a straight trend line, but an S-shaped trend line, one that flattens out at either end of the income scale. We would just want to take a slightly different look at the results of that. If you look at the lower end of the income scale, down around $37,000 to $57,000, the left end of the scale, you see that it's a fairly flat increase in probability of purchase, going up $20,000 from $37,000 to $57,000 in the income, according to this regression equation and according to the data that we've presented to it, does not increase by very much at all the probability of acquiring a house. Presumably, the family or the person who is contemplating purchasing the house needs more than $60,000, possibly even to qualify for a mortgage loan. At the other end of the scale, the same sort of thing is going on, up around $157,000 at the right end of the income scale. You see that, once again, the trend line is fairly flat, and a difference of $20,000 between $137,000 and $157,000 does not increase the likelihood that the person will purchase a house. There are all kinds of reasons that might be the case. Perhaps the person already has a house, and getting an additional $20,000 in income is not going to convince him or her to go out and buy another one. On the other hand, in the middle of the scale, say around $100,000 in annual income, the jump in the probability of purchase is fairly dramatic, going from, let's say 97,000 to 117,000. There we're increasing as much as 20% just from an increase of $20,000 in annual income. Now, this is the kind of thing that we would expect. The logic of the situation tells us that an increase in income of $20,000, whether you're at the low end of the scale or at the upper end of the scale, is unlikely to make much of a difference to your probability of purchase. However, in the middle of the income range, right around 100,000, say 97,000 to 117,000, an increase of $20,000 in annual income does apparently result in a fairly sharp increase in the probability of purchase, just as we would expect. So the fact that we're able to create an S-shaped curve here rather than a straight line or linear trend line enables us to get a more sensible, logical result from the projections that we are looking at than would be the case with the straight line curve. And in Chapter 2, we'll start taking a look at how using odds rather than probabilities assists us in creating the desired shape of the curve that we're looking for rather than the straight trend line that we're settled with given standard linear regression. You're very likely aware that there's a close relationship between probabilities and odds. And you can think of the probability as one of several equal slices of a pie. In this example here, we've got a pie with 5 equally sized slices, each of them 20%. The probability is represented by, in this case, a gray slice consisting of 20% of the pie, and then 4 slices of 20% each that represent the opposite of whatever the event that has a 20% probability is. So in this case, we've got 4 slices against the event, 1 slice for the event, and so we wind up with odds of 4 to 1 against. Now, obviously, there are plenty of other odds that you can cite. And in this case, for example, we've got 10 slices, each of them 10% of the entire pie. 1 gray slice of 10% represents the likelihood of an event occurring, and the other 9 slices represent the 90% that the event will not occur. And so we wind up with 9 to 1 odds associated with a probability of 10%. Of course, it's also possible to get equal odds when the probability is 50% that an event will occur, then the probability that it won't is also 50%, and we wind up with 1 to 1 or even odds. There is an easy way to go back and forth between odds and probabilities. The equations are down here in row 14. So you can take the probability and divide it by 1 minus the probability to get the odds. So in the case of, we'll take 75% probability of success on row 9. Well, we take a probability of 75% and divide that by 1 minus 75%. So we wind up with 75% over 25%, and that's 3 to 1. Or in row 5, again, a probability of success of 20%. And if we divide 20% by 1 minus 20%, we wind up with 20% divided by 80%, and that's 0.25 to 1. Now, if you want, you can switch the order there of 0.25 to 1. So you've got 1 to 0.25, and that's what takes you to against success. And you can multiply both the 0.25 and the 1 by 4 to get rid of the fraction. You wind up with 4 to 1 against. You can go the other way as well and change the odds to probability. Let's take 3 to 1, for example, on row 9. Our odds are 3 to 1, so we take 3 divided by 1 plus the odds, or 4. 1 plus 3 is 4, and 3 divided by 4 is 75% probability of success. We'll take a closer look at probability and odds in the next lesson. In cell M2, I've repeated an equation from the prior lesson, and this equation relates the probability to the odds. Note the right-hand side of the equation to the right of the equal sign, where we're dividing odds by the total of 1 plus the odds. This is an important equation. because if the odds, no matter how high they are divided by 1 plus the odds, that means that the probability can never achieve more than 100%. If the odds are as much as 100, let's say, then 100 divided by 101 is always going to be smaller than 100%. And yet we can convert those odds to a probability, and the probability will, in any case, always be less than 100%. So by forecasting or predicting odds rather than probabilities, we get around the problem that we discussed in earlier lessons of winding up with a probability that's greater than 100%. We'll show how we get accurate predictions while preventing the predicted probability from falling below 0%. And at that point, we'll have achieved our initial goal of restricting the projections and predictions for probabilities to between levels of 0 and 100%. If it's been a while since you studied logarithms, a brief refresher probably wouldn't be out of the question. Let's take a look at how logarithms work very basically in this lesson. A logarithm is really just a power or an exponent to which you raise another number. And that other number, if you're talking about the natural logarithms, is this number here, 2.71828. And actually, it's an irrational number, so it goes on forever. But the logarithm is the number following the caret here. So in this case, the logarithm is 4.828, and we raise the base of the natural logarithms, 2.718, to the value of the logarithm to get that number. So if 5 cubed is 125, then the natural logarithm of 125 is 4.828. And Excel has a function called ln, which will return a natural logarithm. And if you take the natural logarithm ln of 125, it will return 4.828 as the log. The base of the natural logs is 2.718, as I mentioned, and the exp function returns the antilog. So if we take 125 and then submit 4.828, that is the logarithm, to the exp function, then it will return 125, which is the original number up here that we started with to get the logarithm of 4.828. So the ln, the natural logarithm function, gets you the logarithm. The exp function returns the antilog, and you give it the logarithm, and it returns the number that you originally started with. Now, there are some extremely useful ways to use logarithms in logistic regression. For example, let's say that we had the number 512 and we wanted to multiply it by the number 1,296. Well, it's a little bit tedious to carry out that multiplication. If you use logarithms, you can take the log of 512, known as ln of A3, and A3 is 512. And if you add to it the natural log of 1296, ln of C3, then you get a sum of 13.405. And if you now raise the base of the natural logs, 2.718, to that logarithm there, then you get the number that you were originally looking for. So you've got a choice between multiplying in a fairly cumbersome way two fairly large numbers, or getting their logarithms, adding their logarithms, and then raising the base of the natural logs to that result to get the number that you were originally looking for. Logistic regression, when you're calculating what's called the likelihood ratio, makes use of this aspect. And of course, as we discussed earlier in the prior lesson, another property of the logarithms is that as the odds ratio moves from 1 down to 0, the logarithm of the odds can then take on negative values, and that makes it very useful as a predictor variable in logistic regression. As I noted in the prior lesson, that highlighted formula there, starting in cell H14, is an important one, relating probability to odds. And in point of fact, its close cousin, right over here, relating odds to probability is equally important. And the reason is that the only way that you can get a negative odds ratio is for the probability to be an illegal value. In other words, the probability has to be either smaller than 0, and that's not allowed, or greater than 1, and that's also not allowed. We don't work with probabilities that are less than 0% or greater than 100%. Now, if you take a look at that formula, you'll see the reason why. For example, let's say that we had a probability of 110%, that is 1.1. Well, if you complete the formula, the divisor is 1 minus 1.1, and the result is minus 11. So that's one way to get a negative odds ratio, but unfortunately, it involves using an illegal value for the probability. Alternatively, if you specified that p is a negative value, let's say minus 0.1 or minus 10%, then the denominator is 1 minus 0.1. And the result of that ratio then is minus 0.09. So those are two ways that you can get a negative odds ratio, but they involve using probabilities that are not allowed. So nevertheless, we want whatever we are predicting in our equation to be able to follow the predictor variable as far down as is necessary. If that predictor variable gets close to negative infinity, well, we want the variable that is predicted also to fall very low, and we can't have it stopping at 0 as the predictor variable continues to get smaller. The way around that is to use the log of the odds, that is the logarithms of the odds ratio. And over here we can take a look at how that works. Here we've got a series of odds that are sorted in ascending order from 1 in 10,000 all the way up to 10,000 to 1. And notice that as the odds on success get smaller and smaller, the log of the odds gets smaller and smaller. We do not have a negative odds ratio, which we just demonstrated involve using a negative probability or a probability that is greater than 100%. We do not have that with this, and yet the log of the odds can fall as far below 0 as is necessary to keep up with the predictor variable. And therefore, what we want to do is use the log of the odds as the variable that we are predicting. Once we have gotten the log of the odds predicted, we can convert the log of the odds via a function called the antilog back to the odds ratio, and then, of course, we can use, once again, these equations to move from the odds ratio to the probability. And we'll take a look at how all of that works out in the next lesson. At this point, it'll be useful to see how all these piece parts that we've discussed so far come together in a full logistic regression analysis. Before we do that, let's just take a quick review of the two Excel functions that we discussed in the prior lesson. The logarithm, in fact, that in Excel could be the natural logarithm using the function ln to return it, and the natural logarithm 512 is 6.238, and therefore the base of the natural logs, 2.718, raised to the logarithm 6.23 equals 512. And you can get the antilog by using the exp function. So if you know what the logarithm is, 6.23, you can submit the logarithm's value to the exp function and get the number that you were originally working with when you got the log. Now, these are functions that are native to Excel. Although you can find logs and antilogs as functions in the R application, their arguments are different, their names are different, and just in general, you use them a little bit differently. They will return the same values. My point is that in order to see what's going on with a logistic regression analysis, it's a lot easier to tell what's happening if you can look inside the black box, and the best way to do that I know of is to look at it in Excel. Now, R is a lot faster. You'll get a logistic regression analysis from R with a lot less effort than goes into a logistic regression analysis done in Excel. The other side of that coin is that there's an awful lot of information that R doesn't show you because it's really intermediate calculations. My contention is that if you understand what those intermediate calculations are, you'll have a much better understanding of what logistic regression is all about. So that's why we've been going through all of this in the context of Excel. We're about starting the next chapter to start using R to return the logistic regression with a lot less effort and a lot more quickly. But here's how it comes together in Excel. What we've got here is a somewhat different example than we've been working with in prior lessons. Our outcome is whether or not a person gets the flu. And we have a new vaccine that we're testing, and we want to test different milliliters of that vaccine. And we want to test it against people of differing ages, and we want to test it against males and females to see if there's a sex-related difference in terms of who gets the flu having been administered the vaccine at a given age. Now, for those three independent variables, milliliters of vaccine, the age of the patient, and the sex of the patient, we have coefficients, just like we do in a standard multiple regression analysis. We also have an intercept, and just like in a standard multiple regression analysis, we add the intercept to the product of the milliliter coefficient times the number of milliliters, plus the age coefficient times the age, plus the sex coefficient times the sex. And we wind up with what's called the logit. Kind of the same way that bit is short for binary digit, logit is short for the logarithm of the odds. And as I just mentioned, the formula is the intercept plus the dosage beta, which is what I've called milliliters, times B6, which is the actual milliliters for this particular patient, plus the age beta times C6, plus the sex beta times D6, and the result is the logit. You come up with these coefficients and the intercept by using what is called solver in Excel. It's a maximum likelihood add-in that's pretty easy to run and surprisingly powerful. So we can get the ideal, the optimum values for the coefficients and for the intercept by applying solver to the problem, and it will come up with those values. We get the logit. And now over here, we use the antilog to change the logarithm of the odds to the odds themselves by using the exp function. And then we can back finally into the predicted probability by using the formula to calculate the probability from the odds right here. So this is our end result for the logistic regression analysis. Although I call it the end result, we're not really through with it because we want to be able to assess the reliability of the logistic regression equation, and we'll be doing that starting in the next chapter. Previous lessons have discussed some of the building blocks of logistic regression, such as odds ratios and logarithms. Let's take a look now at how to assemble those pieces so that we get a set of predictions from logistic regression. Keep in mind that R does all this automatically on your behalf, so that's convenient, but you can't see most of it, and so it's hard to tell really what's going on behind the scenes. Excel, on the other hand, leaves it all visible to you so that you can see what's happening, but it takes a lot longer. So when you're used to it, it's time to move over to R, and we'll show how that's done before this series of lessons is through. The layout that you're looking at on this worksheet includes fictitious data on a pharmacological experiment regarding a flu vaccine. And you see in column A whether or not the person gets the flu. And then in columns B, C, and D, we have some predictor variables, the vaccine dosage, the number of milliliters that were administered in the shot, the person's age, and the person's sex. One male, two female, or vice versa, it doesn't matter. The idea is to determine whether the vaccine's ability to prevent the flu varies as a function of dosage, age, and sex. And notice that the outcome variable in column A, whether the person gets the flu or not, is either a 1 to indicate, yes, the person did get the flu, and that represents a 100% probability, or 0 to indicate, no, he didn't get the flu, a 0% probability. And I've left a few blanks in rows 1 through 3 at the top of the worksheet, and they'll be filled in shortly. So let's go now to take a look at the actual coefficients. And here we see the actual intercept and the milliliters of the dosage, the coefficient for the person's age, and the coefficient for the person's sex. Our goal is to develop an equation that looks like a standard regression equation. It'll have an intercept and coefficients that we use to multiply the observed values in rows 6 and below on the predictor variables, dosage, age, and sex. And the intercept and the coefficients will occupy cells A3 through D3, just as shown there with 1s and 0s at present. And to make the interpretation easier, I've named the cells. For example, cell A3 is named intercept, and you can see the name of the cell in the name box here on the formula bar. I've named cell B3 as dosage coefficient, or dosage coef for short. Age is age coef, and sex is sex coef. If you're not familiar with how you name cells, it's something that if you're a routine Excel user, you'll want to become familiar with. You do so by choosing the Formulas tab in the Excel user interface and then coming over to the Defined Names group and click on Define Name, and you can use the information in this dialog box to name a cell whatever you want. It turns out that it's useful in the development of formulas and equations that rely on those cells. Also notice that I've initialized the values of the intercept and coefficients in row 3, 2, 1, and 0. Those are not optimal. They're just standard kinds of initializing values, and we'll use Excel Solver shortly to optimize them so that we get the best equation that we can. Now, we want to assemble the logit at this point, and the logit, of course, is the log of the odds, as we've discussed in prior lessons. It's the direct result of applying the logistic regression equation to the observed predictor values. For example, this value of the logit in cell E6, if you look in the formula bar, is the intercept plus the dosage coefficient times the value in B6, which is the milliliters of the vaccine that this person received, plus the age coefficient times cell C6, and that's the coefficient times the person's age. Finally, we add the sex coefficient times the value in D6, and that's the person's sex. And next, we'll take the predicted logits that you see in column E and convert them to probabilities via antilogs and via the simple odds to probability formula that we've discussed in prior lessons. Those probabilities are compared to the actual 1s and 0s, or 100% and 0% in column A. And Excel Solver will use the difference between the projected probability and the actual probability to adjust the coefficients and the intercept in A3 through D3 to bring the predicted probabilities as close as possible to the ones that were actually observed. Now, notice that the initial logits in column E present all equal 1, and that's because of the current values that I've assigned to the intercept and the coefficients, 1s and 0s. So the intercept is defined as equaling 1, and at present the coefficients for the dosage in millimeters, the age, and the sex are all 0, so the result of adding those in the equation are also 0, and the logit there must return a 1.0 at present. So next we'll look at moving from the logit to the probabilities. Now, it's easy to go from the logit to the odds. You just use the EXP function. For example, in cell F6, notice in the formula bar that the formula given is equals EXP, and the argument to the EXP function then is the value that's found in E6. And the result is to get the odds that are based on the logit calculated in cell E6. Now, notice that the odds are all temporarily set to 2.718. And this is because the logits are all temporarily set to 1.0, as we discussed in the prior lesson. That's just a function of the coefficients and the intercept that I've already initialized them to. The antilog of 1 in cell E6 is 2.71828, and that's the base of the natural logs. So what we're doing is we're submitting a logit of 1 to the exp function, and that automatically will give us that value for the odds. The logit, of course, will change as soon as we change the coefficients in the intercept. Now, we still need to get from the odds to the probability, and that's just a function of using the simple arithmetic formula for the probability. We take the odds and we divide by 1 plus the odds, and that gives us the probability. But that probability needs to be adjusted. And here we've got temporarily the coefficients and the intercept that have been optimized. You'll see shortly how to get that done, but I've taken care of it here so that we can discuss the probabilities a little bit more sensibly. In cell G6, the active cell, we see that the predicted probability, given those coefficients and intercept, that the person will get the flu is only 2%, which is good in as much as the person did not get the flu. Notice in cell A6 that he's got a 0. Now, this is a large part of what we want, but it's not quite all of it. We also want the probability that each person has the predicted outcome, and that will help us evaluate the accuracy of the equation. We already have the probability in column G that the person will get the flu, but we need to adjust the probability that's in column G to account for those people who don't get the flu. So in column H, we use the formula that you'll see here. If A6 equals 1, that is, if the person did get the flu, then use the probability that you find in cell G6. Otherwise, if the person does not have a 1 in cell A6, use 1 minus G6, which is the probability that he did not get the flu. And again, that's the actual outcome in this particular case. So the next lesson discusses how to assess the accuracy of the overall regression equation. At this point, we want to start assessing the quality, the effectiveness of the logistic regression equation. And to do that, we're going to evaluate the goodness of fit between the predicted values and the actual probabilities, the ones that we actually observe. And we're going to look at their continued product. I'll get around to the meaning of a continued product in a moment, but consider the implications if we could predict the outcomes perfectly. In that case, all the probabilities in column H would be 100% or 1.0, and their continued product would be 1.0. The continued product is simply the product of the probabilities. If we were to get the continued product of the existing probabilities in column H, we would multiply 0.2689 times 0.2689 times 0.2689, and so forth throughout the rest of the data set. If these were all 100% or 1.0, meaning that we had predicted the outcome perfectly, if that were the case, then their continued product would be 1.0, the product of all of those probabilities. Now, bear in mind that the logarithm of 1 is 0, and therefore the log of the continued product is the sum of the logs of the individual probabilities. So if those individual probabilities are 1.0, we would have for each of them a logarithm of 0. And if we add up those logarithms, we would wind up with a sum of the log likelihood that equaled 0. So the continued product of all perfect predictions is 1.0, and the sum of their logs is 0. What we would like to do is select an intercept and coefficient in cells A3 through D3 that get the total of the logarithms as close as possible to 0. And that's the logarithmic equivalent of a continued product of 1.0. To optimize those coefficients and the intercept, we use Excel's solver. One thing to bear in mind is that this use of the logarithms in the context of the continued product and the sum of the log likelihoods, this usage is completely different from the use of logarithms with the odds ratios. The idea with the odds ratios is to allow the log of the odds to fall well below 0 if necessary in order to follow the predictor variable's value all the way down. And then we take the analog of the logit to get back to above 0 for the odds. Here, though, we just want a convenient way to evaluate the accuracy of our predictions. And so we totaled their logs in cell I3 It's labeled sum log likelihood. And we make whatever changes to the intercept and the coefficients. We make those changes via solver. And we make the ones that are needed to bring the total of the log likelihood as close to 0 as possible. And we do that in cell I3, where the formula is actually the sum of the values in I6 to I41. So how do we go about optimizing the coefficients? We're going to use solver. I've set the original values for the intercept and the coefficients to 0. The sum log likelihood at present is minus 33. To run solver, you would choose the data tab on the ribbon, and once you've selected that, go to the right end of the ribbon and make sure that you've got an analyze group here with the link to solver in it. If this is missing, then you're going to need to install solver in Excel, and you may want to contact your IT person for assistance with that, or do it yourself if you feel comfortable with doing that. I can tell you that the process starts by choosing File and then choosing Options at the bottom of the nav bar. And you may well be able to follow the trail of breadcrumbs to get to the point where you are going to actually install solver. If you already see the Analyze group and solver on the ribbon, then you're home free as far as installation is concerned. And I would suggest that you start out by choosing the cell where the sum of the log likelihood is calculated. In this case, that's cell H2, and then choose solver. The objective cell is cell H2, and that's the point of starting out by selecting it before you invoke solver. So we're going to want to set this objective to the maximum value. And in this context, the maximum means closer to 0 instead of closer to minus 100. We're starting out with a negative value here, and to maximize it, we want to move it as close to 0 as we can and not away from 0 toward minus 100. We'll do so by changing the variable cells A3 through D3, and that's the intercept and the 3 coefficients. We're not going to constrain any of those cells, although we could do so if necessary using the subject to the constraints area here, but we're just going to leave that alone. The Make Unconstrained Variables checkbox, we'll leave that unselected. You'll want to choose the GRG nonlinear method of solution. And once you've got that selected, please click the Options button and choose the GRG Nonlinear tab. What you want to make sure here is that the central derivatives option button is chosen, and we'll make sure that the require bounds on variables is unselected. You don't want to put bounds on these variables at this point. And then click OK to get back to the solver parameters dialog box, and you click Solve. And just that fast, solver found a solution. All constraints and optimality conditions are satisfied. We'll want to keep that solution. Notice before I dismiss this dialog box that the intercept and the 3 coefficients have been set to new values. We don't want to return to the solver parameters dialog box, so just make sure that cell is cleared and click OK. And now we have optimized the coefficients and the intercept, and the sum of the log likelihood, which had been something like minus 33, is now minus 14. It's a lot closer to 0, and that's telling us that the predictions are a lot closer to absolute accuracy than they started out. At this point, we can check the value of eliminating some of these variables. Perhaps one or more of these coefficients could go away, and we would have an equally accurate prediction without burdening the data with an unnecessary variable. So we'll take a look at comparing those models in the next lesson. This is the model that we came up with at the end of the prior lesson, and all 3 predictor variables are present in the logistic regression equation. The model's sum of the log likelihood of minus 14 is considerably closer to 0, which would imply a set of perfect predictions, than when all we had was an intercept of 1 and coefficients of 0, and thus the variables were not in the equation. Question remains, does it really help us to use these variables, dosage, age, and sex? We could conceivably drop them from the analysis and just go with an intercept all by itself. So the question is, does the use of the predictor variables, dosage, age, and sex, make a dependable difference to the accuracy of the equation? If we were to take a different sample of 20-odd people and put them through the same experiment, would we get a similar outcome to the one that we've got here? Another way of asking that question is, what is the statistical significance of our finding here? Well, one of the ways that we can use to check that is by using what I'll refer to as a restricted model, as distinct from the full model that we've got on this worksheet. Now, in this restricted model, I have constrained the coefficients for dosage, for age, and for sex to be 0. In other words, just basically drop them out of the equation and use the intercept alone. Now, the intercept is just a scaling factor. It's possible now to calculate a sum of the log likelihood using the intercept alone and not using dosage, age, and sex as part of the equation. The result is that we get a sum of the log likelihoods of minus 0.24. Now, that's a lot further away from 0 than we had in the full model, where we had a sum of the log likelihoods of minus 14. So we know that we've got a better prediction from the full model than from the restricted model, but can we depend on it? Can we depend on getting a sum of the log likelihoods of minus 14 if we were to take a different sample of cases? And one way to do that is to test the increment. So in this worksheet, I've taken the log likelihood for the restricted model, and we got a minus 24, and the log likelihood for the full model of minus 14, taking the difference between the two, and we've got what's called a delta log likelihood of minus 9.89, or almost minus 10. Now, in many instances of testing statistical significance, we take an obtained statistic and we compare that obtained statistic, such as delta LL, to a reference distribution, such as the normal curve or the T distribution or the F distribution. But it turns out that the delta log likelihood does not follow one of those familiar reference distributions. On the other hand, it also turns out that if you multiply the delta log likelihood by minus 2, you get a variable that in fact does follow the chi-square distribution. And once we've multiplied it by minus 2, we get a quantity that is conventionally referred to in logistic regression as minus 2LL. Sometimes people refer to it as G, sometimes people refer to it as the deviance. But in any case, whatever term they're using to refer to it, it's the number minus 2 times the delta of the log likelihood. And in this case, we get a value of 19.79. Now, we can submit that value to the chi-square function in Excel, which is chi-square.dis.write. And once we do that, we get a probability of obtaining the value as large as 19.79 from a chi distribution with 3 degrees of freedom. Those 3 degrees of freedom represent the 3 variables that we dropped out of the equation in the restricted model. So by constraining those 3, we get 3 degrees of freedom for the chi-square test, and we find that we get a value as large as 19.79 only twice in 10,000 times, given that the chi-square distribution has 3 degrees of freedom and that the 3 variables, age, dosage, and sex, have no effect on the probability of getting the flu. So our choices are themselves restricted. We can either choose to believe that we got an extremely unlikely outcome just by chance, or we can come to the conclusion that the 3 variables that we used in the full model do in fact exert an effect on our ability to predict whether or not a person would get the flu. That's a much more likely outcome than 2 in 10,000. So we'll adopt the conclusion that the coefficients and the variables do in fact make a difference.